we're going to call this volumes with known cross sections. You guys know what a cross section is? You ever heard that term, a cross section? Like, a cross section is, think about food. So here's this roll of paper towels. Here's a stack of paper towels, right? A cross section is if you take your solid and slice it. Like this, pretend this is a loaf of bread, okay? If I slice this loaf of bread, what's the piece of bread going to look like? Like it's going to be like a wafer or a donut, right? If I slice it this way, it's not, I don't know what it's going to look like. I guess it'd be kind of rectangular shape. Like if I think about this as a loaf, the cross sections of this, you know, if I slice it like that, the cross sections would just be that shape right there. This kind of rectangle, but it's kind of got a little curvy top to it. Like pieces of bread that you would slice off of this loaf would be funny, right? Does that make sense what a cross section is? It's all about how you slice, right? So let's just think about a region here. And if I draw a region, let's say that looks like this. Okay, so this function right here, we'll just say it's like f of x. Okay? And then I'm going to say this is x equals a, and this is x equals b. And so that's the region that we're going to talk about. So before, what we were doing is we were taking that region and spinning it around an axis. Right? And when we spin, that creates circular looking things, right? They were either washers or discs or donuts or, or one of those things, right? But now what we're going to do is we're going to build a solid where this region right here is like the base of the solid. That region is like the bottom that you would like sit on the table. Right? And then the solid is going to have these differing cross sections where if I slice it, we're going to have these different pieces. Okay? So like the first one we'll do is where the cross sections are squares. Okay? So like what that looks like here. It's going to look something like this. Okay, so there's the region. Now I'm drawing this three-dimensionally. So now when we say the cross sections are squares, they're going to look something like this. So do you see there? Can't do that wrong. These pieces are square slices, like a piece of Kraft singles cheese. You know what I mean by that? You ever seen Kraft singles cheese, American cheese? Like little squares. I missed that one, didn't I? So the question is now, if that's now everybody has to visualize this somewhat. The solid, the region that we're talking about is like the bottom. So I'm going to slice this thing, and all the pieces are going to be craft single pieces of cheese. Right? And I'm slicing it perpendicular to the x-axis. All right? So now I'm thinking about, okay, what's the volume of now that solid? What's the volume of that solid? Well, can you tell me what the volume of one slice would be? Well, how thick is this? How thick is that slice? It's going to be dx thick. Do you see that it's dx thick? Because it's this, if you think about this this line, this length right here that I just drew, that length right there, where is that length over here? Right there. Okay? And when that length is vertical, how thick is it? Always dx, right? Okay, so it looks like this if we're going to draw it regular, right? So it's dx thick. What are the sides of that? What are the sides of that slice? How long is this? These two are the same, right? Since that's a square. Just this length right here, right? Which in this particular case, that's just f of x, right? So the volume of one slice would just be f of x times f of x times dx. Or f of x squared times dx. So that's the volume of one slice. One piece of cheese that's infinitely thin. What's going to be the total volume? How can we find out the total volume? What do we have to do? Integrate. Add up all the pieces. Right? So if we add up all the pieces, that's going to give us the total volume. And that's going to equal what? And then we just add them up from x equals what to what? A to B. Okay? So to help you visualize this a little bit better, maybe, okay? If you look up here, I've got two curves. I've got an f of x and a g of x, right? What's that length right there? F minus g, right? So now, if I do a cross section of squares, we put the lights. I might be able to see these pieces a little bit better. I don't know if you can see them that great, but do you see the little individual squares there? Yeah, that makes it a little bit more clear. I made and the number of squares smaller to help you visualize it a little better. So if the red is F and the blue is G, what would be the volume of this solid? it would be exactly the same thing as this, except instead of f of x there, what would we have? F minus q. Okay? Because it's all about this length right here. Right? All right, let's do another one. Let's kind of use the same our picture here, and we'll go over there in a minute. Let's do isosceles right triangles. So we'll have the same region. Okay? But now when I slice this baby, instead of a square slice like we had before, I'm going to have a isosceles right triangle. Okay, so let me draw this on there just so you can see another one. You can't see that, can you? So what's the volume of one of those triangular pieces? I feel like this is like Subway cheese. You go to Subway, don't the cheese pieces come as triangles? I don't remember if they're equilateral triangles or isosceles triangles. What's going to be the volume of one of those? Of one slice? What do you think, Abdel?
F of x times dx over 2.
F of x times dx over 2. Okay, how'd you get that?
The volume of the triangle plus the volume of the square over 2.
So if I draw this triangle, this is dx tip, right? So what's the volume of that triangle, Abdel?
F of x times d of x over 2.
F of x times what?
Dx over 2.
So this length right here is f of x, right? I feel like you're missing a dimension. You said it's 1/2 f of x, which is that length right there, times dx. So you're missing, it's 1/2 f of x, it's base times height is the area of that triangle times the thickness. So what's this side right here? Like what's this side right here? If it's isosceles. Yeah, it's f of x, right? So f of x times f of x times 1/2 times dx. Right? Or 1/2 f of x squared times dx. Does that make sense, Adele? Does everybody see that? Why it's 1/2 f of x times f of x? The area of the triangle is base times height divided by 2, right? The 1/2 base times height. And an isosceles triangle, the base and height are the same. Or in this particular one. So what's the total volume? You would add up all those pieces. From x equals a to x equals b. Right? Do you see that the answer that we would get for this one, or the solid that we drew, is exactly half of the other one that we just had? It's like as if someone took a knife and just cut through this one at a 45-degree angle, cut it in half. Okay, my little sketch thing doesn't make the isosceles triangle, so. Okay. What about equilateral triangles? What's that going to look like? There's a region. So now the pieces are equilateral triangles. In fact, I have to draw this one another way. Can't draw it the way I just did the last one. So now the slices, here's our region down here on the floor, okay, on the base, and the slices are equilateral triangles. So that, and that are all the same length. You got another one in there. I could have made that bigger, couldn't I? Let's draw with that. There's the equilateral triangle, right? How long are those sides? They're all that same length. What's that length? F of x. Okay? Now, if that length was determined by two different curves, it would be like f minus 2, like it is over there. Okay? So all of these are f of x long, right? How thick are they? They're dx, because we're really slicing this. These are really triangular pieces stacked like library books. Whereas these were triangular pieces stacked like library books. Or before, when we had the craft single squares, those were craft single squares stacked like library books. We're stacking like library books with dx, right? But what's the volume of one of those slices? It's going to be the area of that triangle. What's the area of that triangle? Uh-oh. Base times height divided by 2, right? So it's f of x. What's the height of that? That's an equilateral triangle. Do we know how to do that? Well, if you forget, I mean, some people might just have that memorized. I don't. What are all the angles in an equilateral triangle? 60. Oh, okay, so I can do that. 60, 60, 60. Right? So I know that the sine of 60 degrees is equal to h over f of x, the hypotenuse. Like I'm using this right triangle right here. So what is the height? It's the sine of 60 degrees times f of x. So what's the volume of one slice? 1/2 base times height. Or, if you wanted to clean that up, 1/2 f of x squared. Does anybody know what sine of 60 is? We could just leave it like sine of 60 if you don't know. Sine of 60 is, no one knows? Okay. That's sine of 30. So if I just told you that's sine of 30 and he said 1/2, then you got to know what's the other one. There's only two numbers that you got to work with, right? 1/2 or radical 3 over 2. So what's the total volume? I do need the dx. Thank you. You would have caught that. Because what's the dx, Becca? The thickness, right. This right here is just the area of that cross section. This is the thickness of it. So that makes a volume, because area times thickness is volume, right? So now add up all the total, or all the pieces to get the total volume. What's it going to be? So 1/2 f of x squared times radical 3 over 2 dx. What do the semicircles look like here, or the equilateral triangles look like over here? See that? And if I make more of them. That's kind of fun. What's the last one? Semicircle. So now when you slice this solid, like it's a big hunk of cheese, you're going to get semicircular slices, like provolone or something. I think provolone is semicircular shape. All right, so what's that going to look like? Oh, here's our region again. So what's that going to look like if we slice this and get semicircular? Oh no! That's what the saw will look like. I'm going to post about 4 problems for you to try on Classroom, but I also want you to see if you can come up with what would the volume of one of those slices be. See if you can do that. That's what we'll pick up tomorrow. I'll also post that link to this little thing so you can see.
Yeah, I think so.
Live like this.
Yeah. Hey, Mr. Mitter.
You got corrections?
Like right now.
Oh, yeah. More than likely, it'll just be set up. But if I don't give you the graph for you, then
Is it gonna be like the?
is that hard?
No.
Yeah, I don't, I mean, yeah. and it'll be-
What?
Norm said your graphs look different than ours.
Oh.
You won't see it. A little bit. So. You feel like the cutoff was here, would be like the PGA golf course. Like you're going into Saturday, the cut line is different every week.
I don't know. I mean, and you also know that passing is not the same as the score needed to graduate.
True.
Because the score needed to graduate was like a 687 or something like that. The passing is technically a 700. That's what it is.
Good.
Are these red? Yeah. Okay, good phone.
The tender versus nothing all down there.
Yeah, I think it's like more stressful. Doing what? Oh, I can know. The hospital bed?
Hello, everyone. How's everyone's spring break? You in Florida? So everybody went, the whole fans, both fans?
Megan.
No, Megan. She not on spring break?
No, they don't have one. They don't have that one.
Did they not get a spring break?
But she went.
They just get classes?
I don't know.
Or did they have, are they online?
She has like, it's like hybrid, I think.
Yeah, I guess if your classes are online, why not? What do you want? Come in during the day, watch your class. All right. Did you get burned? Do you burn easily?
It depends. How long it's been. I didn't burn the first day.
Anybody else do anything fun? So did Megan.
Yeah, we were together.
Oh, you went with, oh, I don't know if she said that. Yeah, you got a hot tub. Yeah, that's great. Very good. And you had nice weather because you were there last weekend. Not this past, but during the week. The weather during the week was fantastic.
Yeah.
Do you know anybody else do anything fun? What'd you do?
I think that was very good time.
For soccer?
Yeah.
Did you see Mr. Callahan there? You knew that was the science teacher? He was there, right? All right. Anybody else do anything fun? I didn't know. I went to the dance. So, my dentist retired. So like, and he sold his practice. So like now we just walk in there and it's, everything's all new. The lady, you know, when I walk in, who knew my name for 20 years, I go in there. Like she knew when I was done. Like, oh, you want to make your appointment for next time? She knew what time school got out. She knew I wanted to have the first appointment after school got out, so I would be able to not have to miss school. They don't know that. It's all new. Okay. Yeah, that's about it. Billy, what did you do?
Me and Gavin and Odell hung out. We went to Westchester, went to IKEA.
You went to IKEA? What are you guys, 40?
He sent you a picture when we were reading at no, like some piece
That's
of
where we
like.
were at. Oh, is that when you guys were, when we were talking about
The odds of winning rock, paper, scissors.
Oh, yeah.
50-50 is like 33.
Yeah, I still think it's one third.
But then once you hit, there's only two people. So wouldn't it be 50-50?
But didn't you write out all the possibilities?
No. You
told
just
us
have a
to.
pen and an accent.
Then just ask the waiter.
It
Or the
was like,
waitress.
we were already there. Like,
They're like, hey, can you borrow your pen and an accent? We got some math we have to settle. They love that stuff. I went to a restaurant in Oxford, Ohio, or not in Oxford. I went to Oxford last weekend for a swimming for my daughter. And we just had to drop her off. Like there was no spectators. So we dropped her off at Miami at the pool at like 7:15 in the morning. And we had to kill 4 or 5 hours. So we drove up to College Corner, Indiana, which is a town that half of the town is in Ohio and half of the town is in Indiana. The high school there, it's actually, I think, a 7 to 12 building, has kids from 2 different states and 4 different counties. So, like, you could live in Ohio but go to this high school in Indiana. Because the high school, literally, half of it is in Ohio and half of it is in Indiana. In fact, the basketball court, the half-court line is the state line. So when you're playing a game there, you're half the time you're playing in Ohio, half the time you're playing in Indiana. And a long time ago, when Indiana used to not do the same time as Ohio, they were in a different time zone, they had a clock on both ends of the basketball. One of them was an hour behind the other. Because it was Indiana time and Ohio. Now Indiana's on the same time, so. But we went into this little tiny restaurant in College Corner, Indiana. That's probably about the size of this classroom, maybe small. This is at like 8 o'clock on a Sunday night. We walk in there, and everybody in there, well, first of all, no one's wearing masks, which didn't really expect that. Everybody knows everybody. I mean, in fact, we're the only people in there that, I mean, we look like we stuck out of deer in headlights, you know, just sore thumb, like, just, you know. We walk in there, we're the outsiders. County sheriff's in there. He's talking to us. While we're sitting there, the phone rings. There's probably, total number of tables in the restaurant, probably like 10, 12 maybe. And there's like, maybe about half of them have people out. While we're sitting there, the phone rings. And there's only one waitress taking care of the whole everybody. The phone rings while we're there. She answers the phone, and it's some guy calling the restaurant to have someone there go pick him up so he can come hang out with everybody else. Like, he didn't have a ride. He must have been an old guy, can't drive. Because she gets on the phone and she's like, hold on, and then she's like, I can't remember who it was. She's like, so-and-so, he wants someone to come pick him up. And they're all like, well, I don't want to go. I don't want to get him out. And then someone's like, okay, I'll go. And they got up and went to go pick him up. Drive out in the country to pick him up. So he can come drink coffee and tea out in his place. How fun is that? It's like nostalgia. But they have these little coffee mugs that have like little advertisements on them for like little local businesses. And I was like, I really like these mugs. So I asked the waitress, can I buy one of those mugs from you? So he So if you're in the need for J&S Mechanical, they do heating, air conditioning, drain cleaning, got a phone number, Liberty, Indiana, call Ross Outdoors, Bath State Bank, Hometown Wholesale, where you're always welcome. I don't even know what that is, but yeah, so that was it. You guys went to IKEA?
Yeah, they shut tonight.
But why did you go to IKEA? Why not?
It's just fun.
Yeah, Billy bought a chair, a couple plants, some boogers.
I mean, this is really partying up on your spring break.
Well, we found like my old collection of this, and then we turned on.
Did you hit up Bed Bath & Beyond while you were out?
No.
Maybe a Home Depot?
You haven't shown me the border. Like, I did some like red dots.
I didn't get to though. He came upstairs and Mr. Dark. I couldn't see him. And I vanished the restaurant.
Oh my gosh. Funny stuff. And then you probably watch some basketball. Right?
Nobody's saying anything.
What?
Yeah.
This is a crazy tournament.
Unless you actually get up. Who do you think's gonna win?
I mean, I still think Gonzaga or Baylor are probably. I mean, I would love to see Oral Roberts go, but I don't know that it's going to happen. Although who's their next game? Who's Oral Roberts have next? I feel like I remember looking at the bracket thinking, oh, their next game may not. They might win again. It's possible because I don't think they had a Yeah, I don't think they have like one of the super high seeds. But who knows? Who knows? Who knows? All right, so here's the plan. We're going to talk about, we sort of alluded to this last time I saw you. We talked about these other types of volume problems. We're going to talk about another type of volume problem where we're using integration. And then tomorrow we're going to have a little quiz, very quick quiz on discs and washers. And not with this is really willing to do. Just discs and washers. Which is kind of like what the Delta Math assignment was. That many of you did, but a few of you did not do. So yeah. So we feel good about that? I said it might be, yeah. So I guess I feel bad. It's gonna, some people didn't do it. What do we do? Just give those guys zeros? That's what somebody in last period said. It's their problem if they didn't do it.
Yeah.
You made your bed. Lie in it. Yeah, so maybe I'll extend that deadline. I'll think about that here after we're done. Put a plan together. So what we're going to talk about now is what we call volumes with known cross sections. Now, it's interesting, but a lot of people in your world are not familiar with the term cross section. Anybody not familiar with that term? Cross section? Anybody know what it means? Okay. Maybe you've heard it before, but you don't know what it means. So it's helpful to demonstrate cross-section with something three-dimensional. So like this is a solid, right? A cross-section is what happens if you look at this solid and you slice it. What are the slices going to look like? So like here's a solid, right? And it's pretty uniform. Like if I slice this solid, like what are the pieces going to look like? If I slice them like this. What? Like donuts, okay? Flat donuts, right? Or a washer. If I slice it this way, what are they going to look like? Well, if I slice it this way, they're going to actually look like rectangles for a while until I get to where the hole is. Okay? Here's the difference. This is like so a cross section. You got to think of like a cross section. Is like if you have a loaf of bread, what are the slices look like? So if this is a loaf of bread from like Big Sky or something, if I slice it this way, what do the cross sections look like? Well, they look kind of rectangular with these rounded tops, right? But if I slice it this way, they would be rectangles. Okay? So what we're going to do now is we're going to create solids, not by revolving a region and making it like a solid that way. We're going to create solids by building up cross sections, okay? So like if I draw this picture, okay, and I'm just going to call this f of x here. And I'll call this A and B. What we're going to do now is we're going to think of a solid where that region right here, like before we were taking this region right here and spinning it around an axis, right? Now we're going to think of that region as the base of a solid, as like the bottom of a solid that you can put on the table. And then we're going to slice it and have these various cross sections, okay? So the first one we're going to look at is where the cross sections are squares. And I should say perpendicular to the x-axis. Okay? So now we're going to think about this solid is going to be a bunch of squares that are stacked like labels, side to side, perpendicular to the x-axis, and they're going to be squares. So what's that going to look like? Well, it'll look something like this. That's a terrible drawing. I'm going to draw it again. So I'm embarrassed by that. Draw it again. So do you see, here's the region, and here's like the region, flected down to make it three-dimensional. And there's a square piece. A square being like a piece of Kraft single cheese. Did you see the square? Let me highlight it with another color. Okay? So the first question I have for you is, if those squares, if we're slicing it like this, okay, perpendicular to the x-axis, how thick are those pieces going to be? They're going to be infinitely thin, but which infinitesimal are we going to call it? Dx or dy? Dx, okay? And we know that and how we know that is because of this rectangle right there not rectangle. That line right there that I'm drawing is that line right there. And when that length is vertical, it's dx thick. That's how we've always done it, right? If I draw one of these squares now, now I know that's dx thick. What's the side of the square? What's the side length of the square? It's f of x. It's this length right here, right? That length right there corresponds to that length right there, and also that length right there, since it's a square, all four of the lengths are the same. So now, kiddos, what's the volume of one of these slices? What's the volume of a piece of cheese? What's that going to be? It's going to be f of x squared times dx, right? So what does that represent? That represents the volume of any one of those slices for some particular value of x. How do I find the total volume? How do you find the total volume? We're going to add up all the slices, right? From where to where? A to B, right? How do we add them up? We integrate. Remember, integrating is adding up a bunch of stuff. Here we're adding up a bunch of pieces that have that volume, which gives me a total volume. Okay? Now, over here in this GeoGebra sketch that I've got going on the board, okay, and if you're watching this online, I'm going to put a link to this GeoGebra sketch in the classroom so you can play with it. Instead of the region being defined by one curve, now I've got a region being defined by two curves. So everything is going to work the same here, except that length right there is that length right there. And then when you have two curves, what's that length right there? If the two curves are called, say, f and g. F minus g, right? Okay? So what does this look like if I've got cross sections being squares? Okay, do you see the squares? And now I can add lots of them, and then that's what the solid is going to start to take some shape. Okay? That make sense? Okay, so let's try another one. Let's do isosceles right triangle. Same region. What are these babies going to look like? So do you see the isosceles right triangle? Oh, you got an answer for me already?
Is it just 1/2 of the square?
Exactly. Okay. You're seeing this It's as if I took this square and I just sliced that solid with a big knife at a 45-degree angle, right? But if we build it up, the volume of one of those pieces is going to be 1/2 f of x squared dx, and then the total volume is going to be, add up those pieces from A to B. Okay? What you need to be thinking about here, guys, so important, that you think about, when I go to write that interval, what is it that you're adding up here? Okay, you should always be thinking about that. You should never really write an integral symbol without thinking about what is it that I'm adding up. Okay? There we're adding up pieces that are isosceles triangles. Okay, let's do another one. Let's do equilateral triangles. So there's our region. Now when I slice this, the pieces are going to be equilateral triangles. What's that going to look like? Okay, so here's the region. I flipped it on its side. So there's the region right here. Okay, now do you see the slices? There's the triangle there, there, and maybe another one. I'll draw it in red so you can see it. So if I draw one of those cross sections, it's an equilateral triangle. How long is each side? What do you think, Mia? If it's equilateral, they're all the same. It's f of x, right? Because like if, it's all about that length right there. And that length is f of x. So this is f of x. This is f of x. This is f of x. Right? But what's the volume of one of those slices? What's the volume of that? Now, how thick is it? Still dx, right? But in order to find the volume of that triangular piece of cheese, I used to use like Subway. There's like a way to describe this, Subway cheeses. But the kids last period, they looked at me like I had two heads. So I kind of go to Subway anymore. Except Goski. point of swimmers in those things. Gospel gets subway every day. Remember that?
Yeah.
What did I say? Gospel. Oh my God. Woski, yes. I went to college with a guy named Brad Goski. That's what I said. Woski, sorry. Yeah. Woski. Yeah. So Woski would know what I'm talking about when I say this. Goski, Brad Goski. I haven't seen him. 30. I think the Subway cheeses are triangular shaped, except provolone. It's semi-circular.
Yeah.
Which we'll do that one here in a second. What's the volume of that thing? You know it's dx thick. What's the area of that triangle? We're gonna have base times height. Well, shoot. What's the height of this? It's not f of x, kiddos. Now, do you remember how to find the area of an equilateral triangle? Probably not. But if push came to shove, could you find it? Well, you could use some weird version of the Pythagorean theorem because if you remember, the altitude of an isosceles triangle bisects the base. So this is half of f of x. This is f of x, and then this side here. So you could do Pythagorean theorem. Good call. You could also use basic trig because you know each of these angles are 60, right? So the sine of 60 is h over f of x, right? So what's the height? It's f of x times the sine of 60. Okay, so what's the volume of one of those triangular pieces? Hello? Bill, you know?
Okay.
1/2 times
F of x sine.
times. I got that.
Times it.
Yeah. Right. So let's clean that and just make that 1/2 f of x squared times the sine of 60. Billy, do you know what the sine of 60 is? Like if I was going to hit you over the head with a 2x4, if you didn't tell me the answer to the
I
sine.
mean, I can find it.
I got all day. Not one, it's the other one. That's the sine of 30. The sine of 30 is 1/2. So it's right over here with 2. Oh, I forgot dx. Oh no. That's the volume of one triangular piece, yeah? So what's the total volume? 1/2 f of x squared times radical 3 over 2 dx. And add that up from A to B. Okay, so what's equilateral triangles look like over here? Okay? Basically, the formula for this picture over here is going to be the exact same, except it's just going to be f of x minus g of x. Because it's all about this length. This length is the important thing. It's all about that length. equilateral triangles. What's that? Isn't that neat? Okay. All right, now let's do provolone. Probably my favorite cheese. Although the white American's pretty good. At Subway. But the provolone is delicious as well. Semicircular. So what's that going to look like? Well, our region ain't going to change. Now, when we slice this loaf, or this block of cheese, we're going to have these perfect semicircles. What's that going to look like? Oh, baby. So, friends, what's going to be the volume of one of those semicircular slices? The volume of this provolone. Maybe we should draw it. Oh, that was horrible. What is the radius of that semicircle? It's 1/2 f of x. The radius of that is 1/2 f of x. Or, over here, 1/2 of f minus g. Okay, so how thick is the cheese? Still dx, right? Like always, since we're stacking these up like library books. So what's the volume of that slice? Pi r squared dx. Huh? That's not it. Because that right there would not be a semicircle. That would be a whole circle, right? So we would need to multiply this by 1/2. All right, so what's the total volume? Add up the pieces. From A to B. Now, if you were to clean that up, you would end up with pi over 8. It turns out that total volume is the same as the square, except it's multiplied by pi over 8. Like the very first example that we did. Do you see why? I have said before, maybe in this class, I don't know, So I remember when we talked about, I think I did tell you guys, when we worked in 5th grade, volume is really nothing more than what? What are we doing when we find these volumes? We're integration, but what are we adding up? Or what are we stacking? Slices, right? But it's stacked area. Each one of these formulas that we came up with was basically this. What did A of X mean? It was the area of whatever the cross section was. Right? That's what volume is, people. It's stacked area. Integration just gives you a way to find volume when the area is not constant. Like, yeah, in 5th grade, you learned how to find the volume of a cylinder, right? What did you do? You found the area of the base times by the height. Or you found the area of the prism. What did you do? It was the area of this times the length. Right? You were integrating. You just didn't know it. Okay? Is it time to go? So check on the Google. I got about 6 problems for you to try. That's all on this. We have a quiz on discs and washers tomorrow. And then we're going to start something new. Remember I told you we're not going to do the shell method. Skipping that. So, see you later. Have a nice day. Oh, yeah, are those Adidas shorts? I have those same shorts. Well, are those black? Mine are blue. I really like them. See you later.